Bonjour, I'm Hexacon, and also known as Xiaobye. I'm currently working at DevCore as a security researcher. Today, I'm going to present a comprehensive security study of MediaTek Wi-Fi, from Wi-Fi MCU firmware reverse engineering to vulnerabilities in Wi-Fi kernel module. And finally, demonstrate how we exploit the beacon vulnerability to achieve remote code execution in a Wi-Fi router. So why MediaTek? Since its Wi-Fi chips are widely used in various products, such as Sonos speakers, Amazon Echo, Starlink Wi-Fi routers, and many other famous devices. However, most research has mainly focused on Qualcomm and Broadcom chips. And detailed study on MediaTek Wi-Fi chips remain limited. So far, only 3 studies are somewhat related to MediaTek Wi-Fi chip security. But 2 of them barely mention the chip architecture. Bad Mesher only discusses issues related to easy mesh. And Listen Up mostly focuses on Sonos devices. Unlock hidden superpowers in MediaTek Wi-Fi chips is currently the most detailed study on reverse engineering and architecture presented at NorCon in September this year. There wasn't much information available, so we got curious about the security of MediaTek's Wi-Fi implementation. In our research, we will focus only on remote attack surface. Okay, let's begin our journey. In this chapter, we will demonstrate how we reverse engineer MediaTek's Wi-Fi MCU. In this picture, we show an overview of Wi-Fi stack. The orange parts represent components related to Wi-Fi protocol stack. The Wi-Fi physical layer turns bits into signals to send and back into bits when received. The MAC layer controls access to physical layer and handles the encapsulation and decapsulation of Wi-Fi frames. The MLME is the core module responsible for handling MAC layer management. It mainly processes management frames, maintains state machine logic, and handles control operations. The LLC forwards data frame to upper layers, typically carrying protocols like IPv4, IPv6, ICMP, and so on. The supplicant and authenticator handle Wi-Fi authentication and key exchange. After seeing what the Wi-Fi stack looks like, let's take a look inside the MediaTek Wi-Fi 6 router. It can be separated into 2 parts. The MT7981, which is an Wi-Fi SoC, and the MT7976, which is an radio frequency chip. The Wi-Fi SoC is made out of an application processor and 3 Wi-Fi MCUs. WA CPU and WL CPU are related to transmission and aggregation. We haven't studied them in depth, so we won't cover them here. Today, we only focus on the application processor and WM CPU. The WM CPU mainly manages the MAC and physical layer and receives Wi-Fi frames from the Wi-Fi radio. The application processor runs the Linux kernel, which includes a kernel module called mtwifi.ko. This module interacts with WM CPU firmware to receive Wi-Fi frames and issue commands to let the WM CPU to manage the MAC and physical layers. So how does the WM CPU work, and how is its firmware load on it? Also, what ISA does the WM CPU use? We need this information to move forward with our reverse engineering. At boot, the Wi-Fi kernel module is loaded and initialized. It then starts loading firmware into the Wi-Fi MCUs. Here, we take the WM CPU firmware loading as an example. First, it parses the ROM patch header. And then loads the ROM patch into the WM CPU memory based on the header. Let's take a look at the important information provided by the patch header. The build date field shows when the ROM patch was built. And in this case, it is built at 2023, July 28. And a field that indicates how many regions are in the ROM patch. In this case, there is only one. So the ROM patch includes only one region header. The header of the region 0 is shown on this slide. The load address of region 0 is hex 90,000, and its size is hex 2580. After loading the ROM patch, the Wi-Fi kernel module then parses the header of RAM firmware. It then loads the firmware into WMCPU memory based on the header, and finally triggers WMCPU to jump to the entry point to execute the RAM firmware. The RAM firmware header is different from the ROM patch header, and it is located at the end of the file. It also contains a build date, which is pretty close to that of the ROM patch. It also has a field to indicate the number of regions. In this case, there are 11 regions. The RAM region header of the RAM firmware comes before the RAM firmware header. In this slide, we show the load address, region size, and region feature of region 0 and 10. The region 0 has its feature set to hex 20, indicating that the load address of this region is also the firmware's entry point. After analyzing the WMCPU loading process, I gained an initial understanding of the WMCPU memory mapping, but what I thought does the WMCPU use? We gripped firmware and found many useful strings. In particular, the WOCPU firmware contains paths which reveal that WOCPU uses the MDS32 architecture. Therefore, I guess that the WMCPU uses the same architecture. To validate our guess, we use the MDS32 processor patch from Ghidra staging, built Ghidra with MDS32 support, loaded the WMCPU into Ghidra, and set the base address. Next, we pressed D on the undefined bytes, and the disassembly result made us really excited. It looked very complete and confirmed our guess that the WMCPU also uses the MDS32 architecture. Next, we loaded the firmware and ROM patch into Ghidra and ran the built-in analysis with aggressive instruction analysis. We noticed that many functions reference unaffect GP, which refers to global pointer register. It is used to indirectly access global data. Since Ghidra didn't know the value of the GP register, many strings and functions cannot be interpreted correctly. After searching in Ghidra for a long time, we still couldn't find where GP was set. We guessed that the ROM on the MCU might contain the data we were looking for. So we decided to take a different approach. I tried using the debug commands provided by MediaTek and found some useful commands, such as enabling WMCPU, debug logs, and memory access command. However, the command I was most interested in was the core dump command, because it dumps the entire runtime state, including some regions that were not present in the firmware or ROM patch. After loading the core dump into Ghidra, we finally found where the GP register is set. Next, we modify the value of the GP register. Now, every indirect access via GP is correct, and we have a complete human-readable decompiled output. I started looking for vulnerabilities. There isn't much code handling frames, and I quickly found a stack overflow. This vulnerability is exploitable. There is no stack canary, no data execution prevention, and the memory mapping is fixed. Everything goes back to 2008. We can directly return to shellcode. Sounds pretty good, right? I tested the exploit on my testing device, It worked, and I could observe it executing shellcode in the core dump. However, it didn't work on other devices. The exploit didn't crash devices with the same chipset. But how? I'm confident that the testing devices I used was updated to the latest version, which was released on December 22. Although it was released on December 22, it still contained an older version of WMCPU firmware, which was built on July 22. After further investigation, I collected firmware from various sources and found that this vulnerability had already been patched in the version released on October 24. So what I found was an end day. Here is a fun fact I learned from the lesson, but it wasn't fun for me. Device vendors update firmware, but sometimes they skip the chipset vendors' patches. I had to spend a huge amount of time to hunting down different firmware and drivers, and I could never be sure whether what I found was really the latest. Moreover, MediaTek told us that they can't provide the newest SDK to us, only to their customer. So I'm not sure if the vulnerabilities I found are 0 days until MediaTek validates them. We didn't find any other vulnerabilities in Wi-Fi 6 MCU firmware, but that won't stop me. Then what about Wi-Fi 7? Here is an overview of our MediaTek Wi-Fi 7 target. The application processor and Wi-Fi chip are not integrated into a single SoC. The application processor is AM7563, and the Wi-Fi chip is the MT7991, and it also contains 3 MCUs. The run firmware format is similar to that of the MT7981. However, every region in the run firmware has the firmware feature set encrypted. This means all regions are encrypted. But I couldn't find the decryption algorithm in the kernel module or MCU firmware of Wi-Fi 6. It seems that the decryption is handled by specific hardware, so it is difficult to decrypt the firmware. I spent a lot of time but got nothing. Because of this, I choose another way to obtain the plaintext firmware. I use the debug tools I mentioned before to dump a core dump from the Wi-Fi MCU. I simply grab the strings in the core dump to see if they contain the source code paths. And yes, they did. I found that the ISA of the Wi-Fi 7 MCU is RISC-V. We loaded the firmware into Ghidra for reverse engineering. At first, it might seem exciting because many instructions can be disassembled. But as you scroll through, you'll realize it is a disaster. Some custom instructions that represent nothing, and others cannot be disassembled at all. As a result, most functions have incomplete decompiled output. This makes the decompiled code hard to understand because many prologue and epilogue instructions and key operations are missing. Before starting reverse engineering, we need to fix this instruction first. Let's first look at the custom RISC-V instructions. RISC-V provides 4 instruction encoding spaces that can be customized. Vendors can use these spaces to design their own instructions. On this slide, we show the format of R-type custom instructions. Now, the question is, which vendor designed the custom instruction we see in Ghidra? We know that the Wi-Fi 6 MCU is provided by NDIS. Based on our research, the architecture of NDIS latest CPUs is RISC-V. So we investigated the NDIS RISC-V ISA and found a complete specification. We converted the custom instruction provided in specification into slave format and added them to the CPU instructions set in Ghidra. SLAY is Ghidra's processor specification language. It is used to describe the translation from the bit encoding of instructions. We added about 24 custom instructions from specification, which solved the issue with the custom instruction and made most of the code readable. The disassembled output is now much easier to understand. You can see the result after our modification. The custom instructions are now translated into conditional branch. You can imagine how inaccurate the decompiled output would be without these instructions. However, there are still significant issues with the disassembled and decompiled output, and we still cannot perform reverse engineering properly. We observed that there are two groups of instructions that cannot be decompiled. From their partial encoding, we know that these two instructions are RISC-V compressed instructions, each using only 16 bits of encoding space. By checking Andy's manual, we found that one of the instructions belonged to Andy's extension, Cadence, and its instruction name is exec.it, which stands for Execution on Instruction Table. So what is Cadence? As its name implies, it is designed to reduce compiled program size by placing frequently used instructions in the table. The 2-byte exec.it instruction fetches and executes instructions from the table. Here is an example to show how it works. When the CPU executes exec.it, it fetches the corresponding instruction according to its encoding. Then executes the fetch instruction. It's a pretty cool technique from compressing the size of the firmware. So far, we still have one instruction left to resolve. We didn't find the format of this instruction in the specification, so we tried to guess its functionality. The result is that we cannot infer the behavior of this instruction, since the instruction in the firmware doesn't share the same functionality. So we guess that this instruction also belongs to the Cadence extension, but it is not publicly documented. Based on our previous experience with the Wi-Fi 6 MCU firmware, we looked for a function with the same functionality in both Wi-Fi 7 and Wi-Fi 6 MCU firmware to make a comparison. Based on our guess, the instruction should look like this. And the instructions that are actually executed should look like this. By directly searching memory for the executed instruction, we found two instructions separated by 16 bytes. We can confirm that the encoding matches our guess. Next, we try to convert the instruction encoding into SLAY language. However, the SLAY syntax doesn't provide a way to handle this behavior. I and my colleague HexRabbit also attempted to use Ghidra P-code injector to make it decompile correctly, but it didn't work. In the end, we added the comments for the instructions corresponding to Cadence instead. So far, we have transformed the firmware into readable, disassembled, and decompiled code. So I started reverse engineering and found that the code related to frame parsing is similar to Wi-Fi 6, with only few additional functions. But by the end, we didn't find any 0 days in either Wi-Fi 6 or 7 MCU, but we still learned a lot from this journey. The Wi-Fi architecture can be divided into FullMAC and SoftMAC. FullMAC implements most of the Wi-Fi protocol stack on the Wi-Fi MCU, while SoftMAC implements less on the MCU. Apparently, the architecture of MediaTek Wi-Fi should be SoftMAC, and most of the frame parsing functionality is handled by the Wi-Fi kernel module. This story doesn't end here, otherwise I wouldn't be standing here today. Next, I will dive into a much larger remote attack surface. MediaTek's Wi-Fi kernel module. Let's move into a new chapter, the forgotten frame injection. Wi-Fi networks can be divided into two types, BSS networks and IBSS networks. A BSS network is a centralized network where all frames are forwarded by the access point to stations. On the other hand, IBSS is an ad hoc network where stations communicate with each other directly. In the following slide, we only focus on the BSS. Unlike Ethernet, which requires a physical cable to a switch, Wi-Fi can access by anyone within signal range. Therefore, it needs an authentication mechanism to protect the private Wi-Fi network. So far, Wi-Fi security protocols have evolved through WEP, WPA, WPA2, and WPA3. Today, most Wi-Fi access points can't enable WEP, and users shouldn't use it either, since its key can be cracked in minutes. The latest protocol, WPA3, is now available, but according to Wigo.net, WPA2 still accounts for around 75% of networks, while WPA3 is used only about 3%. From WPA to WPA3, each have personal and enterprise versions. The personal version uses a pre-shared key, which is basically a Wi-Fi password. It is the most common method in daily life. Take WPA2 as an example. Users who haven't been authenticated can only send APO frames. All other type of data frames, such as IPv4, are blocked. So what is the purpose of APO frame, and why are unauthenticated users are allowed to send them? This is because it is used to exchange information required for WPA2 authentication. It carries data such as nonces and broadcast key. Once users finish WPA2 authentication, they can send any encrypted data frame and freely access the AP's network. In the Wi-Fi kernel module, MediaTek has implemented its own WPA family, as well as the logic for parsing and handling data frames. Verifying if a data frame can be accepted involves several checks, including the LLC format, user authentication, frame encryption, and more. This raises a question. Is it possible to bypass the authentication? It would be great if I could access the AP's network without a Wi-Fi password. And of course, I can. In the MediaTek AP, when receiving data frames, there is a missing check, allowing an attacker to inject arbitrary data frames without being authenticated. The Wi-Fi authentication is still there, but the AP will accept any data frames, whether you are authenticated or not. So how does it happen? In MediaTek implementation, the MCU forwards any data frame to the kernel module, which then decides whether to send it up to the up there. If the source is not authenticated, the kernel module will drop the frame. However, MediaTek also implements an accelerated method for passing and forwarding frames. When the MCU receives a Wi-Fi frame, it first converts it into an Ethernet frame. Next, the Ethernet frame is sent up to the Wi-Fi kernel module. But here, there is no check to see if the source is authenticated, which means anyone can send arbitrary plaintext data frames, and the AP will just accept them. Now, an unauthenticated attacker can do port scan or launch attacks on the AP's network. Your network is now open to everyone, especially malicious actors. This type of vulnerability was discussed in 2021, but still exists in 2025. Threat attacks showed how it can be used to attack computers on Wi-Fi network. I won't demonstrate here. If you are interested, check out this work. You will learn a lot. Next, let's move on to our new chapter, One Friend to Break Them All. The vulnerabilities discussed in this chapter can directly cause a device's kernel to crash, and in some cases, even allow remote code execution. There are many types of Wi-Fi friends, and management friends are the most diverse. By studying how they are parsed and handled, we found several 0 days in MediaTek Wi-Fi kernel module. Most management friends after the fixed header are made up of multiple information elements. Each element has a type, length, and value. Vendors often don't check them properly, making them a major attack surface. Here is the first CVE. It occurs in action frames and is caused by a missing range check on category field when the order bit in the MAC header is set. The category comes right after the MAC header, and the order bit is located within the MAC header. When an action frame is received, the kernel module executes the corresponding state machine based on the category field. On this slide, the state machine for action is shown on the right. The upper green part handles frame processing, while the lower part is used for internal communication within kernel module. In normal operation, action frames can only access the upper green part. The lower part cannot be reached via action frames. However, when the order bit is set to 1, due to the lack of a check on the category field, an attacker can use a Wi-Fi frame to access the internal state machine. This causes the internal state machine to treat the Wi-Fi frame as an internal structure. On a 30-bit system, field size, duration, and frame control are treated as a pointer. You can fully control duration, but frame control can only be partially controlled, making exploitation harder. This is cool vulnerability. Achieving RC is possible, but difficult. However, it can at least cause a remote kernel DOS. Next, let's take a look at our second vulnerability. This one occurs in FT action frames. So what is FT? FT stands for fast BSS transition. This feature helps reduce the long delay when roaming between APs. Using FT can reduce BSS switching delay to an acceptable level. During the FT process, FT action frames are used to exchange key and re-authentication information. The FT confirm action frame consists of MAC header and action header and information elements. When the AP receives the frame, it validates certain IEs by MAC calculation. However, the information elements to be validated can be up to 761 bytes, which causes a heap buffer overflow during MAC calculation. Since it copies IEs into a fixed size buffer, these frames not only negotiate Wi-Fi feature, but can also be used by an attacker to shut down your devices. The next vulnerabilities occur in Wi-Fi 7. The Wi-Fi Alliance officially released the Wi-Fi Certified 7 in 2024. Its theoretically maximum speed is 46 gigabytes per second, nearly 5 times faster than Wi-Fi 6. One key technology behind this improvement is multi-link operation, which is MLO, which lets device transmit and receive data simultaneously across different bands and channels. So how do APs and stations exchange capabilities and information about MLO? The answer is by adding the MLE information element to Wi-Fi frames, so that devices can synchronize MLO parameters with each other. The MLE contains common information and per station profiles. The persistent profile is a sub-element in MLE that describes the capabilities and settings of each link. For example, if a station wants to create a new 6 GHz link, it needs to add a per station profile in the MLE. Both the MLE and per station profile can be fragmented. Let's look at the example. First, the per station profile is fragmented, and then the fragments are put back into the MLE. Next, the MLE gets fragmented, and the fragments are placed back into Wi-Fi frames. When a device receives a fragmented MLE, it first defragments the fragmented MLE. This step includes validation check, so no issues occur. However, when defragmenting per station profile, the fragmented profile is copied into a fixed size buffer without checking the size. An attacker can craft a per station profile larger than 576 bytes, causing a heap buffer overflow. Although Wi-Fi 7 provides higher throughput, it could also bring additional vulnerabilities. This is a last vulnerability. Probe and B conference are related to active and passive scanning, respectively. The main purpose of scanning is to discover nearby APs. Active scanning uses probe frames to check if a specific AP exists, while passive scanning relies on APs periodically broadcasting beacons to surrounding devices. For example, if you turn on the Wi-Fi on your computer, it will start listening to B conference from nearby access points. Here is a shortened pseudocode that highlights just the vulnerable parts. It mainly checks the validity of beacon and probe response, parses each information element, and records them for later use. At first, it goes into a while loop and checks if the information element being parsed can fit into IEBUF, which is 1,024 bytes in size. Inside the loop, if the current information element has a type 244, it is copied into IEBUF. For example, if the frame contains 4 IEs of 244, each 255 bytes long, IEBUF will hold 1,020 bytes after the loop. If an information element has type 221 and is a WSC IE, it is copied into WSC buffer, which has a size of 512 bytes. In the loop, whether copying to IEBUF or the WSC buffer, proper checks are performed to prevent overflow. After the loop, when WSC buffer is copied into IEBUF, no boundary checks are performed. So if it fulfilled IEBUF and WSC buffer in the loop, it will cause a heap buffer overflow at the end. An attacker can broadcast malicious beacons from nearby. Any vulnerable Wi-Fi devices that receive these beacons will immediately go offline. And in the worst case, it can lead to remote code execution. The vulnerabilities I mentioned in this chapter can affect any device that uses the MediaTek Wi-Fi SDK. Many chips share that SDK, so they are not limited to the chips I mentioned today. In the final chapter, I will demonstrate how to exploit the Wi-Fi device with 2B conference. However, I cannot disclose device model information due to the policy of MediaTek's bug bounty program. This is the last vulnerability from the previous chapter, because it can affect multiple versions of the Wi-Fi protocol by broadcasting a Wi-Fi frame. We choose to demonstrate it rather than others. It triggers a heap buffer overflow. The overflow can overwrite up to 508 bytes. And the kernel has nearly no protection mechanism enabled. It is quite common in IoT devices. As a result, exploitation is relatively straightforward. Now, how to debug Wi-Fi kernel module on target device? We couldn't find a way to attach UDP to the kernel, so we had to rely on crash logs. This gives us enough information, but it is a little bit inconvenient. What can I actually control? Local privilege escalation have a lot of options, but a remote Wi-Fi kernel exploitation has far fewer choices. I spent a lot of time hunting for a useful structure, but found nothing. So I kept crashing the devices and collecting state traces for analysis. I found multiple state traces, but the most interesting one is this. So what caused this state trace? At first, the attacker prepared a malicious beacon craft to hijack the free list, and then sent it to victim. Now the free list is hijacked to address A. After that, someone take one free chunk from the free list. Then the attacker prepares a second beacon containing the malicious payload and send it to victim. The victim will acquire the address A and write the malicious payload to that location. If address A is invalid, we get the same state trace we thought before. We currently have a one-shot arbitrary address write primitive. We decided to use it to place shellcode and modify the function pointer in Wi-Fi kernel module. Since there is an indirect code that will execute it. We execute 3 gadgets after the stack pivot. They make the shellcode executable and finally return to the shellcode. Although this vulnerability is exploitable, it takes some time to succeed. Since kernel modules has partially randomized load address and the free list order is not always as expected. As a result, attempts often lead to device crashes. After a crash, the device will reboot, and this allows an attacker to retry. It may take several hours, and attacker could choose to launch an attack at night. Users are less likely to notice, and there is enough time to complete the exploit. Some devices use a monolithic kernel plus driver image with KSLR disabled, which makes them easier to be exploited. Now, let's move on to the demo. The left pane shows the target. The upper right pane is the machine that sends the exploit. For the demo, the Wi-Fi module base address used in our exploit are fixed. Here is what failure output looks like. And after roughly 2 hours of attempts, the exploit finally succeeds. You can see that we executed shellcode which printed a message from the kernel. At the end of our talk, here is our advices for you. For device vendor, you should enable more protection mechanism to increase the difficulty to exploit and continuously track the security update from chipset vendor. For chipset vendor, please share the latest testing builds with researchers under MDA so we can better test the patches. For researcher, there is a large attack surface in the Wi-Fi kernel module and vendor-specific protocols based on Wi-Fi. And you can find the Wi-Fi SDK on GitHub, and it really speeds up the reverse engineering process. For user, strong passwords aren't enough. Limiting Wi-Fi signal leakage can make your Wi-Fi safer. In conclusion, MediaTek follows a clear process for vulnerability handling, and all the issues presented here are already fixed. For more details, see their security bulletin. Okay, thank you for listening.